Hi. So I would like to first start by thanking the organizers for the invitation to the Nearly Carbon Neutral Geometric Topology Conference 2021. And so last year in 2020, in the same conference, I gave a talk on obstructing Lagrangian cobordisms using Hayek-fluid homology. So I thought that maybe this year I'll talk about constructing Lagrangian cobordisms instead. In particular, we'll be constructing upper bounds for the Lagrangian cobordism relation. And this is a joint work with Josh Sabloff and Shay Velovic. So what we're going to do is that we're going to give some background on Lagrangian cobordisms before stating our main results and maybe some applications. So let's start by recalling the basic definitions of context-free manifolds. A context-free manifold is a three-dimensional Y with a two-plane field Xi that is totally non-integrable. We usually, in fact, assume that Xi is the kernel of a one-form alpha. So in the case of R3, that gives us the standard, the most basic example, R3 with a standard context structure where alpha, the one form, is given by dz minus y dx. And let us also recall the dichotomy between tight and over-twisted contact manifolds very quickly. Over-twisted contact manifolds satisfy an H principle and are not so related to the topology, I guess, underlying topology of the three manifold, whereas tightness really has something to do with the underlying topology. So a link in a context-free manifold is Legendrian if it is tangent to the two-plane field Xi everywhere. So you can sort of think of it as lying on the plane distribution. So now we're going to talk about cobordisms. And in this talk, we will be focusing on cobordisms in the symplectization, which is always R across the three-manifold Y. This comes naturally equipped with a symplectic form, which is d of the derivative of e to the t times alpha, where t is the variable associated to R, and alpha it comes from Y. So this is, you can check that this is immediately a symplectic form. So without further ado, the definition of an exact Lagrangian cobordism from lambda minus to lambda plus is as follows, as defined by Chantraine. It is an embedded Lagrangian submanifold inside in the symplectization. Okay, this is symplectic manifold, so we can talk about Lagrangian submanifold. This seems like a lot of symbols, but what it really means is that the two ends are cylindrical. The end, both the positive end and the negative ends are boring, cylindrical. They are just basically lambda plus and lambda minus translated. Okay, what is interesting is it's only captured in the middle. That's the rest of L. It is compact with what we expect to be the boundary. And the word exact here appears, so we also want want exactness of some kind. So in particular, we want e to the t times alpha when restricted to L to be exact. So if it's exact, then it can be written as df, and we further require f to be constant on the two cylindrical ends. In particular, constant and not just locally constant, because we want f to be constant so that we can compose these cobordisms. So I often get asked why we want this exact condition, and maybe the best answer is that you can have Lagrangian cobordisms that are not exact, but then there's just too many, right? Like it's not constrained enough. Then in that case, you're asking a very different question, and it may be one that is less related to the topology. Okay, so what is the easiest way of constructing Lagrangian cobordisms. So there's a class called Decomposable Lagrangian cobordisms, which are just products of elementary cobordisms as defined by Chantrain and also Ekholm and Kalman. And basically, these Legendrian these elementary cobordisms are what you expect them to be: Legendrian isotopy, births and saddles. So Legendrian isotopy can be represented in R3 by Reidemeister moves, and birth is the top picture here. You see that nothing becomes an max TB unknot, and saddles are given by moves like this. This is the minus side. We always take this from here to from left to right. So this side is the lambda minus, and this side is the lambda plus. Now, we often call the lower this second move, the saddle move. Also, we also very often call it a pinch move. But really, pinch is only the right word when you think of it in the opposite direction. Like you're taking the positive side, the positive side, pinching it to get the negative side. But then the cobordism is from the left-hand side, from the negative side to the positive side. So you're going backwards. In any case, you have to note the direction of these arrows. You cannot reverse these arrows. In particular, there is no Legendrian death. You notice. So that in any case, that's these are the elementary cobordisms, and if you compose them, then you get the class of decomposable Lagrangian cobordisms. So we expect that, well, in smooth topology, we know that every smooth cobordism is decomposable into births, saddles, and deaths. Right? That's very basic. So we might expect the same to be true for Lagrangian cobordisms. Well, it's a little bit more complicated. First of all, decomposable Lagrangian cobordisms are exact, so we don't have to worry about the exactness condition. On the other hand, conversely, we might want to expect that exact Lagrangian cobordisms are all decomposable, but that is an open question, and in fact, one of the major open questions in the field, because it's a very basic question to ask. Is every exact Lagrangian cobordism decomposable? We don't know. All right, in any case, let's go back to just Lagrangian cobordisms in general. So I want to give a few more properties of Lagrangian cobordisms. So first of all, if you have two links that are Legendrian isotopic, then you expect there to be a Lagrangian concordance between them. A concordance, by the way, is of course a cobordism of genus 0. There's some subtlety here, which is that you cannot just take the trace of the Legendrian isotopy. You have to do something to it. But in any case, you get a Lagrangian concordance. Fine. And Lagrangian concordances are automatically exact. Nice. Now there's one key aspect where smooth cobordisms and Lagrangian cobordisms are quite different. In particular, for smooth cobordisms, given any pair of knots, let's say, there always exists a smooth cobordism in between. In fact, there exists many different smooth cobordisms in between, all of different genus. And but to find a minimal genus is hard because it's hard to find a minimal genus between any pair. The situation for Lagrangian cobordisms is kind of opposite. You don't really know whether, very often, you don't have existence. So why is that? Chantrain proved that if you have two knots in R3, and they're related by Lagrangian cobordism, then the Euler characteristic of the Lagrangian cobordism, in particular the genus, is fixed by the difference of the Thurston-Banneker numbers of the two Legendrian knots. And so that immediately tells you that a lot of, if you just pick a random pair of Legendrian knots, it's likely that you cannot find there does not exist a Lagrangian cobordism in between. But when it does, you immediately know it's genus from this formula. In particular, we also know that Lagrangian cobordism cannot be inverted whenever the genus is non-zero. Because of this formula, you cannot, this is non-zero. So, well, you can ask, can we invert Lagrangian concordances? That's the only thing left to ask. Well, unfortunately, Chantrain also showed that that is not true in general. You cannot invert Lagrangian concordances. And that means that in particular, Lagrangian cobordisms and concordances are not equivalence relations. All right, great. So they're not equivalence relations. So we just trivially have a preorder. Now, just quickly to recall, a preorder is something that is both reflexive. So lambda, there's this Lagrangian cobordism from lambda to lambda. It is also transitive because you can compose Lagrangian cobordisms. And you might hope, okay, if a preorder is not an equivalence relation, then maybe you can hope for it to be a partial order. Like a preorder would be a partial order if it's also anti-symmetric, which means that in this context, if lambda 1, if there's a Lagrangian cobordism from lambda 1 to lambda 2, and also one from lambda 2 to lambda 1, then lambda 1 and lambda 2 must actually be the same Legendrian knot. Well, we don't know whether that is true. So, okay, we now just have a preorder. We don't even know whether it's a partial order. Can we even say anything about the preorder? So that's really the topic of this talk. So, our main result is basically that under this preorder, you can always find upper bounds for any finite collection of Legendrian links. So here goes the theorem. Suppose that you have two lambda and lambda prime. These are oriented Legendrian links in a tight contact free manifold, and they have the same rotation number. Okay, that's key with respect to some Seifert surfaces. In particular, in R3, they have the same rotation number. Then they will have a common lower bound lambda minus and a common upper bound lambda plus, meaning there exists cobordisms from lambda minus to lambda plus, and also from lambda minus to lambda prime to lambda plus. So sort of forming a diamond from the common lower bound to a common upper bound. In fact, this common lower bound was established first by Miranda, Trainer, and Yan. And so this statement is really about the upper bounds. So here's an example. On the left, we have a trefoil. On the right, we have the 5-2 knots. And there cannot exist a Lagrangian cobordism between them in either direction because they have the same Thurston-Benneken number. Since they have the same Thurston-Benneken number, any Lagrangian cobordism between them must be a concordance, but there doesn't exist a topological concordance between these two knots. So it's not possible. But they have a common upper bound, and here's the common upper bound. And we'll see how to get this common upper bound in a few slides. Here's another example. On the left, we have the max TB unknot. On the right, we have the figure 8 knot. And also, again, there cannot be a Lagrangian cobordism in either direction. The figure 8 knot has TB lower than the unknot, and so there cannot be one in one direction from the unknot to the figure 8, and in the other direction, you can use normal rulings. There are two normal rulings for the figure 8 knot, and so they cannot have the other. You cannot go the other direction either. But again, they have a common upper bound, and then their common upper bound is this slightly intimidating looking link. Again, that means that there is a Lagrangian cobordism from the unknot to this link, and also from the figure 8 knot to this link. The three colors here, green, black, and blue, are just to distinguish the different components of the link. They don't mean anything. All right, so in fact, I want to just mention that we actually prove a slightly stronger statement, which basically says that the Lagrangian cobordisms from lambda minus to lambda plus and lambda minus to lambda plus that passes through lambda and passes through lambda prime, these are in fact isotopic as exact Lagrangian cobordisms. Okay, so this is what we really prove. And I also want to mention that there is a version for unoriented Lagrangian cobordisms. I'm not going to go into details for that. Okay, so maybe a quick sketch of the proof. So the proof is inspired by Oleg Lazarev's recent result for where he established upper bounds also for Legendrians as well. But then he was establishing upper bounds for Legendrians for formally isotopic Legendrians in contact manifolds of dimension at least 5. He uses some H principles there, which cannot be extended to dimension 3, which is why it's for dimension 5 and above. Okay, so for dimension 3, which is the case that we're in, we have to do something different. But the idea is similar. The idea is to first find a common lower bound lambda minus. In this case, we're going to do some pinching. Well, in the case of R3, we already have this result, this common lower bound, just from Branda, Trainer, and Yan. But in any case, we have this common lower bound. And our key insight is to record the cobordisms from lambda minus, the common lower bound, to lambda and lambda prime by Legendrian graphs each, by a Legendrian graph each, I think. Okay, so what that means is the following. So on the left here, we have a case where we're pinching. Let's say we pinch here, and we get to the bottom picture with with the black arcs and the bottom picture. We can record this cobordism, this pinching cobordism, by this Legendrian arc that is red in middle. Okay, and I claim that this sort of encodes this cobordism, this simple cobordism here. On the right-hand side, let's say we pinch at 2 different places. Let's say we pinch first here and then here, down to the, this is the Hopf link. So in that case, we can record this cobordism by 2 Legendrian arcs. So a Legendrian graph is like a Legendrian link, but it can have points where the incidence is more than 2. So for example, at this point, incidence 3, at this point, incidence 3, at these 4 points, incidence is 3. So, and with Legendrian graphs, we can also manipulate them with randomizer moves in R3. Okay, so the key insight is to record the cobordisms by these Legendrian arcs to get a Legendrian graph. And the claim is that you can actually recover the cobordism, because what does it mean to record the cobordism? We claim that we can recover the cobordism by doing Legendrian ambient surgery. Now, this has been written by multiple authors, in particular, for example, by Dimitroglu Rizel, and by other authors as well. There's one word of caution, which is that we don't know how to do this for all cobordisms. Okay, so there are cases in which we don't know what to do. I mean, I want to say that there is no way to do it, but maybe I should just say that I don't know how to do it. So here's one such case. Let's imagine I pinch the inner pair and then I pinch the outer pair. You cannot pinch the outer pair before you pinch the inner pair, so there's an order there. I can record the inner pair, the pinching of the inner pair by this Legendrian arc in the middle. And if I further pinch, I can record the outer cobordism by this Legendrian arc here. But now I have a problem. In the bottom picture, I do not know how to draw a second arc, so that if I do surgery on both of those arcs, I get the top picture. In particular, before I do this outer, before I recover this outer cobordism, I don't know how to do the inner cobordism. So I don't know how to draw that arc. So there is some technical issues there, which means that we have to take extra care to make sure that the cobordisms that we're trying to record are recordable using Legendrian graphs, our methods of recording. In R3, this means that we cannot just directly use the Boranda trainer Yen diagrammatic, front diagrammatic approach. We will still use it. You can still use the front diagrammatic approach, but we have to refine their algorithm to make sure that what I described just now doesn't occur. If you have a general tight context structure, context-free manifold Y, then you have to do something a little bit more sophisticated using convex surface theory. I'm not going to go into detail here, but that's what we have to do. Now, after we have these two Legendrian graphs, one for the cobordism to lambda, the other one to lambda prime, then we can combine the two Legendrian graphs into one Legendrian graph, and that will build for us both lambda plus and the cobordism to it, the common upper bound. So here's the key example. So you can imagine that you take the left hand side here. That is the trefoil, and if you pinch once right here, you can record it by the red arc. Okay, so you get a picture like this. Forget about the green arcs. Okay, then that's just that is recording our cobordism from the bottom picture to the trefoil. And you can do the same thing for this side. If you pinch right here, you can record it by a green arc. Okay, so you now have two different pictures in the bottom, one with the red arc, one with a green arc. Now you can combine them into the same picture here with both the red and the green arc. And now if we do surgery on both of these, do Legendrian ambient surgery on both of these, then you can get to a common positive lambda plus, a common upper bound, because it will go. You can do these two Legendrian surgeries in different orders. I can first do the red arc, in which case I'll go through the left side, or I can first do the green arc, in which case I'll go to the right hand side. Okay, these two don't intersect each other, so they're just far away from each other. All right, so here's a more complicated example. On the left here is the unknot. You can pause the video here for 10 seconds to see that it's the unknot, and on the right hand side we have the figure 8, and in the bottom here the common lower bound is a stabilized unknot. If you do the red surgeries here, then you get back the unknot on the left. If you do the green surgeries here, you get back the figure 8 on the right. And now if you do both, you will get the top picture. There's one more. So this is how we got this intimidating looking link in the first place. Now, if you want a knot at the top, then you can actually do that. It's very easy to just sort of reverse pinch up to a knot. Okay, so that's our main theorem, but I want to talk about some applications now. So one particular application is that we can use our result to define a notion of genus between Legendrian knots. The problem we've been having is that given any pair of Legendrian knots, very likely there isn't a Lagrangian cobordism between them. So how can you define a notion of genus between them? Well, our result allows us to define what we call a Lagrangian quasi-cobordism. So what we really mean is that we can do some sort of zigzagging. Take lambda to be lambda on the left, lambda prime on the right, and we can sort of find a sequence of Legendrian links in between, such that within, between each consecutive pair, you can either connect them by a common upper bound or a common lower bound. And if you just combine, this whole zigzag, common upper bound, common lower bound, common upper bound, common upper bound, and so on, and then you can get from lambda to lambda prime. That is what we call a Lagrangian quasi-cobordism. So here's an example. Immediately on the left, top left here is the unknot, maximum unknot, and on the top right here is the mirror of the 6-2 knot. So these two knots have the same Thurston-Denneken number. I'm sorry. These two knots have yes, that's right. They have the same Thurston-Denneken number, and but then the genus, the slice genus, the four genus of the 6-2 knots is non-zero. It's 1. So by Thurston-Denneken numbers and what we said earlier, you cannot actually have a Lagrangian cobordism in either direction. However, you can find a common lower bound. The bottom two pictures are isotopic, actually. So if you pinch in at this green arc, then you get you can record it by this Legendrian arc here, and same thing on the right. And these two pictures are isotopic, and so you find a common lower bound here. So if you calculate the genus, that's 1. So now you have a Lagrangian quasi-cobordism, and we're going to say that it has genus 1. In particular, we can define the Euler characteristic of a Lagrangian quasi-cobordism to be the sum of the Euler characteristics of all the Lagrangians in between, and define the genus that way. And now, so for example, we just had, as I said, the genus there was 1 in our example. And now we can define the relative Lagrangian genus to be the minimum genus of any Lagrangian quasi-cobordism between the pair. Okay, and immediately we have the corollary from of the main theorem, which says that whenever you have the same rotation number, then any two Legendrian, whenever you have the same rotation number, then they're actually Lagrangian quasi-cobordant. Okay, so there exists some Lagrangian quasi-cobordism between them, because you can find a common upper bound, and our genus, relative Lagrangian genus, would be well defined. All right, so maybe I'll end with some basic properties of the relative Lagrangian genus that we're defining. So first of all, it is bounded below by the 4 genus. It's not hard to prove. So you have this inequality here. And the next natural question to ask is, when is the equality achieved? Well, you know that it cannot be achieved all the time, because if you just consider double stabilizations, that just doesn't work. If you take lambda to be just any link, Legendrian link, and lambda prime to be its double stabilization, topologically they're the same, so the slice genus is 0. But on the right-hand side, by considering the Thurston-Denneken numbers, you see that they cannot be the G sub L cannot be 0. However, in specific cases, for example, when lambda is Lagrangian fillable and has a Lagrangian cobordism to lambda prime, then you can prove that these two are actually equal. So maybe a question to ask is, when else are they equal? So some other open questions that we can pose are the following. Is there a pair of links that are Lagrangian quasi-concordant, but not Lagrangian concordant? Another question is, if lambda and lambda prime are both maximal in terms of Thurston-Denneken number, or maybe let's say they are not destabilizable, then can the difference between G sub L and G sub S be arbitrarily large? And finally, is there a version of this theory is specifically for Maslov zero Lagrangians? And we're asking this because that would allow the use of the Legendrian contact homology. And that is the end of my talk. So thank you very much for attending this talk. And I will see you all very soon.